CERN has done it again. The renowned Laboratory for Particle Physics has announced a groundbreaking discovery made by their Large Hadron Collider, LHC, that could transform our understanding of the universe. Scientists have reported anomalous readings that might signal the existence of extraterrestrial life in a parallel universe. In this video, we will discuss CERN's latest discovery that changes everything. Welcome back to our channel. Today, we dive into an astonishing revelation from CERN, the world's leading particle physics laboratory. The Large Hadron Collider, known for its monumental contributions to science, has once again made headlines with a discovery that could rewrite the laws of physics. Join us as we explore the details of this unprecedented finding, its implications for our understanding of the universe, and the potential existence of extraterrestrial life in a parallel universe. In a recent experiment with the Large Hadron Collider, CERN scientists observed something peculiar with a specific type of quark. Quarks are the fundamental building blocks of matter, and they come in different types, or flavors. Some of these flavors are extremely unstable and decay rapidly. The subject of this particular anomaly was the beauty quark, which has an average lifespan of 1.52 trillionths of a second. Scientists predicted that when a beauty quark decays, it should be influenced by the weak force and transform into a lighter particle known as a lepton, either an electron or a muon. According to the standard model of particle physics, there should be a 50-50 chance for both particles. However, the data from the Large Hadron Collider showed a significant deviation from this prediction. The beauty quark decayed into muons only 70% as often as it decayed into electrons. This anomaly was especially noteworthy because electrons and muons are essentially identical, with the primary difference being that muons are 200 times heavier. Despite this mass difference, the decay rate should remain unaffected. All forces within the standard model are supposed to interact with these particles equally. The unexpected result suggested that a new type of particle might be involved in the process, potentially indicating new physics at play. Currently, the standard model of particle physics is our best framework for understanding the behavior of particles. It describes the electromagnetic force, the strong force, and the weak force with remarkable precision. However, it doesn't account for gravity or explain dark matter, which constitutes the majority of the universe's mass. The unexpected decay pattern observed at CERN hints at the existence of a new fundamental particle, which scientists have dubbed Z prime. This new force-carrying particle could signify the presence of a previously unknown force. Although this force is likely extremely weak, given that it has remained undetected until now, its discovery could revolutionize our understanding of the universe. Physicists are hopeful that if this discovery is confirmed, it could help solve long-standing mysteries, such as the nature of dark matter and the role of the Higgs boson in the creation of reality. Some scientists believe this new force could even lead to the unification of the fundamental forces of nature, a goal that has eluded physicists for over a century. The primary objective of the Large Hadron Collider is to test predictions of various particle physics theories. It accelerates beams of protons and heavy ions, such as lead, to near light speeds and then collides them to create showers of particles. These particles exist for only fractions of a second before decaying, but their brief existence can reveal crucial information about the fundamental forces of nature. The LHC generates vast amounts of data from these collisions, over 15 petabytes annually. Scientists meticulously analyze this data to uncover new particles and phenomena. In 2017, the LHC achieved a significant milestone by permanently storing over 200 petabytes of data, equivalent to around 250,000 movies. The discovery of the Higgs boson at CERN in 2012 was a monumental achievement that confirmed the existence of the Higgs field, responsible for giving mass to elementary particles. The Higgs boson itself is a unique particle that doesn't fit neatly into the categories of matter or force carriers. It was observed in two rare decay channels, into a pair of photons and into a pair of Z bosons. Since then, scientists have continued to study the Higgs boson to understand its properties and interactions. The upcoming high-luminosity upgrade of the LHC, scheduled for completion in 2029, will allow for even more collisions and the production of more Higgs bosons. This will provide researchers with more opportunities to explore exotic physics beyond the standard model, including the search for additional Higgs boson types. The potential discovery of a new force-carrying particle, tentatively named Z prime, carries profound implications for our understanding of the universe. This hypothetical particle could offer insights into the fundamental interactions that govern the behavior of particles such as muons and electrons, potentially reshaping our understanding of the forces that dictate the universe's structure and evolution. In the standard model of particle physics, particles like muons and electrons are fundamental components of matter. They are both classified as leptons but differ significantly in mass. Electrons are lightweight, while muons are approximately 200 times heavier. Despite these differences, they should theoretically interact in a similar way through the weak force, a fundamental force responsible for processes such as radioactive decay. However, the recent anomaly observed in the decay patterns of beauty quarks suggests that muons and electrons might interact differently than previously understood. If a new particle like the Z prime exists, it could be mediating an additional force or interaction that alters the behavior of these leptons. The Z prime could potentially interact with muons and electrons in ways that are not accounted for by the standard model, leading to the observed discrepancy in their decay rates. This discovery could shed light on why particles with similar properties exhibit different interactions. For example, if the Z prime is involved in mediating forces between leptons, it could explain why muons decay differently from electrons. This new particle could thus provide a more nuanced understanding of the weak force and its role in particle interactions. Dark matter, which makes up about 27% of the universe's mass, is one of the most elusive and enigmatic components of the cosmos. It does not emit, absorb, or reflect light, making it invisible to conventional telescopes. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Despite extensive searches, the nature of dark matter remains unknown. The Z prime particle could potentially offer new insights into dark matter. If the Z prime is a force-carrying particle that interacts with dark matter particles, it might help identify the properties and interactions of dark matter. This could lead to a deeper understanding of its role in the universe and potentially guide future experimental searches for dark matter candidates. Moreover, the Z prime could provide explanations for other unresolved mysteries in physics, such as the nature of dark energy, which is believed to be responsible for the accelerated expansion of the universe. If the Z prime is part of a broader framework of new physics, it might reveal connections between different cosmic phenomena that have thus far eluded explanation. One of the most ambitious goals of modern physics is to achieve a unified theory that integrates all fundamental forces into a single framework. Currently, the standard model successfully unifies the electromagnetic force, the weak force, and the strong force, but it does not include gravity, which is described separately by general relativity. The quest for a unified theory aims to reconcile these different descriptions into a single cohesive framework. The discovery of the Z prime particle could be a crucial step toward this goal. If the Z prime represents a new type of force-carrying particle, it might suggest the existence of a previously unknown force or interaction. This could potentially be a stepping stone towards unifying the forces of nature, as it may reveal connections between known forces and the elusive forces that are currently beyond the reach of existing theories. For instance, if the Z prime is found to mediate a force that affects both leptons and quarks in ways not accounted for by the standard model, it could indicate the presence of a more fundamental framework that unites these interactions. Such a discovery would not only advance our understanding of particle physics but also contribute to the broader quest for a theory of everything, a theoretical framework that encompasses all known forces and particles. Confirming the existence of the Z prime particle would be a groundbreaking achievement, offering a more comprehensive understanding of the universe's underlying structure. By identifying a new force-carrying particle, scientists could uncover new aspects of the fundamental interactions that shape the behavior of matter and energy. This discovery could lead to a re-evaluation of existing theories and models, providing new insights into the nature of reality. It could also inspire new research directions and experimental efforts aimed at exploring the implications of the Z prime particle and its associated force. CERN's latest discovery with the Large Hadron Collider has the potential to revolutionize our understanding of the universe. By revealing anomalies in the behavior of quarks, scientists have opened the door to new physics and the possibility of previously unknown forces. As researchers continue to investigate this phenomenon, we may be on the brink of uncovering answers to some of the most profound questions in science.